Okay. So, I'm going to start off by saying that I couldn't tell it. I don't know if y'all could tell, but I think I was in an absolute haze yesterday morning. Because I think I kept trying to say reflection instead of symmetric, reflected across instead of symmetric, and a few other things. And it finally hit me this morning also, because I kept wanting to use also the line y equals x as one of these reflections with the origin. It's not the origin. This is for inverses. Inverses. A function and its inverse are actually reflected across the line y equals x. And I kept saying that for origin, but that doesn't quite work. Because the way that we can think about this, and I can show you this here, because, well, actually, that's a good example. Math for x. So this here is the cubed root of x. Its inverse is actually x to the third. Because if we plug x to the third into the cubed root of x, we get back x, and vice versa. And we get this here, and if I plot that line, let's have it, y equals x, it's kind of hard to see, but we do see that they are flipped over the top of that line. So inverses, two functions are inverses if there's a whole formula to them, but they are reflected across that line y equals x. Now, the way to think of the origin, reflected across the origin, is that we're reflecting it across both the x and y axis. So it's almost, if you see a picture of it, and we do have some, here, if we took this half of the circle, and we flipped it across the y-axis, flip, left to right, kind of line it back up, we'd have a mirror image there. So that's a reflection across the y-axis. A reflection across the x-axis, I don't know why I'm going to do this, flip it up, down. We're just going across the x-axis, so it's reflected across the x. And the origin is saying we're doing both. It's reflected across the x and y. If we do it both and we get points that are on the graph, the original graph, then it's a reflection across the origin, or symmetric to the origin. And that is true with even and odd functions. Because here, as a function is considered odd if it is symmetric with respect to the origin. So what we're saying is, well, let me do this, flip, left to right. I'm putting it back on 0, 0, because 0, 0, when reflected across y, stays the same. So we can say it's not reflected across y because the points on this line don't match up with our original graph. But since it is with the origin, we also have to reflect it across the x-axis, which does give us those points. Does that make more sense than yesterday? Hopefully. Because when we think of a graph of these here with odd, even, neither, even is symmetric to the y-axis. Odd is origin, neither. So if it's even, we're just flipping it across the y-axis. Left and right should look the same, like we see in number 2, the middle one. Odd, we're flipping it across the y, then across the x. So really, it's going to go from here to here, or from this one to this one down here. You got to have that full flip. Hopefully that makes a little more sense with even, odd, x, y, origin. Because, again, it's very tempting. A lot of times, if it is symmetric to both x and y, there's a good chance it's also symmetric to the origin. But there are cases where it's just symmetric to the origin. It doesn't flip both. Oh, back up. Okay, and we talked about this here, plugging functions in. This is where we stop, graphing a piecewise defined function. Now, whenever we talk about these here, there's set points that they start, there's set points that they end. and there's some that continue on in one direction or the other. So if we look at the first function, negative 3x for x less than 1. So that means we're going to use this function whenever the values of x are less than 1. So that means our furthest point on the x-axis is going to be right here at 1. And whenever I look at these here, for each function, I get our points. If we're talking about a parabola, we need 5. If we're talking about a line, we need 2. Absolute values, we're really going to need 3 because we need the lowest point of the v and then 1 point to either side. And kind of have these functions here. Since we do have a line, negative 3x is the equation of a line, linear. We need 2 points. And one of the x values that I'm going to use is the point 1. Now, since we're talking about all the numbers less than 1, we can just pick another number that's less than it and go from there. If this was bounded, I mean, it told us that negative 3 is less than x is less than 1. My two x values are going to be negative 3 and 1. Take the 2 endpoints. But I can pick any points. Since it doesn't have another end, I'm going to pick 0. And now we just need to plug them in. So we can say negative 3 times 1 is negative 3. We can do negative 3 times 0 is, surprisingly enough, just 0. Questions on how we found these 2 points. Now, in Alex, what you can do for the graph is they have array. Because we know it's not a line going indefinitely in 2 directions, we're just using array. And I would start off with, that's 0, 1, negative 3. And you'll pick that as your first point on your array. And with array, you need another point. So we'll pick the point, 0, 0. And at this point here, it should give you the array going all the way off. That's all we have to do. That's one of the nice things with Alex is that he'll actually graph a lot of this for you. You don't have to actually do it all the way out. But there is one thing that we need to do. Is x actually equal to 1 for this here? No. So will this function, negative 3x, actually have a value at 1, negative 3? No. There's another option there that has a little hole with an open spot on it. We'll have to click that and then select this point, and it'll change it to a little open circle. That's really just saying at that point, for this graph here, it's open. It's not included. That's all that's saying. Now we can look at the second one. These here are a little bit nicer. Because for the second part, when x is greater than or equal to 1, we have the function negative 3, yes? Is it going to be any other value besides negative 3? No. Because this here is a horizontal line going across at negative 3. And where's the point it starts at? 1. Because if I did a table, we could say x, y. 1, 2. Well, at 1, it's negative 3. At 2, it's still negative 3. At any value greater than 1, it's going to be negative 3. So we start at 1 at negative 3 and draw a horizontal line. And we can do this with the array again. So we just pick the first point, 1, negative 3, and then just pick some point to the right that's also at negative 3, and it'll draw that line. At 1, is the point negative 3 included? Yes. We could. There is an option to do a closed circle. You can do that. Just having it set up as we have here, it'll also include it. Because the only thing we need to do is exclude those points. So this here would be included. Questions on this here? Now the assignments will also ask about discontinuous or continuous functions. This seems like something new because we may or may not have talked about it specifically in Algebra 2, but y'all have covered it before. If you remember back in probably middle school or Algebra 1 where they talked about having a function and picking your pencil up to graph it, y'all kind of remember that? For some reason they talked about picking it up. And that's what it's really talking about, is continuous and discontinuous. We consider a function discontinuous when you graph it. You have to pick your pencil up at any point to continue with the graph. Essentially, there is a hole somewhere in the function. If there's a hole somewhere in the function, it's discontinuous. If there is no hole, then it would be continuous. So if we look at this here, because I could draw this whole function in one fluid motion, it is going to be a continuous function. There is no hole in it. But that's it. Questions on this here? All right, let's look at this one here. And I picked this one out specifically because of the quadratic part of this function. Now we can start out with the first one here. X plus 3 for x less than -1. So it is a line. And again, the first value I'm going to pick is -1. And then I can pick any number less than it. Because it is a line, I can say -2. I'm just picking 2 points to create this line. So we can say -1 plus 3 is 2. We can do the same thing, say -2 plus 3, which is 1. So we have enough information to draw this graph, yes? So at -1, we are at 2. At -2, we're at 1. And at this point here, if you select the ray, it'll draw the whole line for you. But since it is not equal to -1, since it's just for x less than -1, we need that point, the first point, open, because it's not equal to it. Because if it was equal to -1, we would be looking at the second function, x squared. And we went over parabolas. The first thing we looked for was the vertex, the smallest or lowest point. There's different ways to do it. If it's in vertex form, it's going to be our h comma k. All right, y equals a times x minus h squared plus k. We can use that there. Or we can use the negative b, or b over 2a, to get the x value of the vertex and then plug it back in to get the y. Or, clear. You can plug it into your graphing calculator and see where is the lowest point. For this here, the lowest point is 0, 0, yes? Incidentally enough, if you go second graph, I do have the lowest point 0, 0. And do have 2 points to the left and right. Yeah. The graphing calculator gave me everything I needed. There's 2 points to the left, -1, -2, have the y values of 1 and 4. 2 points to the right, 1, 2, have the y values of 1 and 4. So for this here, our points that we have are -2, -1, 0, 1, 2. 4, 1, 0, 1, 4. Now, for Alex, we need all of this here. We need all these points. Because Alex is still going to want 5 points for a parabola. Out of those 5 points I picked, is there one of them that doesn't work for this here? What is our x restricted to? -1, 2, 2. So this one here technically is not a part of our solution because -2 is less than -1. We wouldn't use the quadratic. We would actually use the other function. Yes? So here we'd really start at this point here because it is the first one that's included. So -1, 1. And that'd be our point. Then we have 1 at 0, 0. We have 1 at 1, 1. Then we have 1 at 2, 4. But does it go past 2, 4? As piecewise function said, we use x squared for x. For -1 less than or equal to x is less than 2. So we don't have anything bigger than 2, do we? So this function goes from here to here. But at that point, it is open. Let me see how this works. Because that would be the final answer. Any questions on this here? And I'll show you one here. I have one pulled up for 2.7 of looking at this because there are ways to delete parts of the graph. Because unfortunately, Alex won't let you just graph the whole graph only that section of the quadratic. It's going to want you to graph the whole thing. So what we have to do is plot these 2 points here, and then essentially use cut or erase to erase the other halves. So you almost have to graph the whole quadratic and then erase the parts we don't need. And before we do that, we'll look at this here. This is the last part of the assignment. The last part of the chapter or section we're looking at is increasing and decreasing and constant. And this, again, this looks very, very complicated, especially the writing. For increasing on I, function I, if f of x1 is less than f of x2, for all x1 less than x2 on I, then it's considered increasing. What is f of x1 and f of x2 really saying? They're just different y values, yes? So that's saying if I picked a y value for one of my x values, go on a graph, I picked this x and this x2. My first one and my second one. And with any point, I have a corresponding y value, yes? So if this y value, f of what would be considered x1, is less than this f of x2. If the first y value is less than the second one, and the first x value is smaller than the second, it has to be going up. That's all it's saying. The same thing's true with decreasing. If the first y value is less than the second, and we're still increasing left or right along the x, then the function has to be going down. And constant, if the y values don't change and the x's are, then it's constant. And that's it. So if we look at this here, and we always talk about increasing and decreasing from left to right. So if we start at the point -4, it is going down. It's decreasing, yes? And it decreases to what point? -1, -2, yes? But whenever we talk about increasing or decreasing, we're purely talking x-axis. What x values is it decreasing? Well, it's decreasing from -4 to -1. Because the point's -4 to -1, it is decreasing. It's going down, yes? Okay. You can leave it there. I'm going to move it up there next to decreasing because that is part of the units or intervals that it is decreasing. But it changes from -1 to 2. It is what? Constant. It's not going up. It's not going down. So constant, we can say -1 to 2. But what happens at point 2? It does what? increases from 2 to 3. And then at 3 it does what? Decreases. When does it stop decreasing? Does it? No, we got an arrow going off to the end, yes? So that would be positive infinity. That's it. That's all we have to do on this here. So we have 2 spots where it decreased. We had 1 spot it increased and 1 spot it remained constant. This is not something that a function has to do. It doesn't have to remain constant. It could be continuously decreasing, or it could be continuously increasing. We could have one or the other, and neither of the other 2. Questions on this here? Because look at one more of those. See here, x to the third. This one here, if we look from left to right, we see that it is increasing, yes? But when we get to the center, it looks like it is going to come to remain constant, but it actually doesn't. This one here is increasing from negative infinity to infinity. The whole function increases. The amount that it increases at the origin is very small, but it is still increasing. This here, so it's the same graph, I just wanted to use it here, because again, even on this one here, it does look like it comes to kind of a constant state at the center. Now, we can see that it is somewhat still going up. The amount that it's going up, we can tell is very, very small, but it is still increasing. So for this here, it is increasing. Because at this point, it's such a small amount of increase, it looks like 0. But for it is increasing on the interval of negative infinity to infinity. It doesn't decrease and it doesn't remain constant. So there are some functions that can increase across all real numbers. If I put a negative in front of it, it would be decreasing across all real numbers. So we could say negative x. And it just flips it, now it's going down. But that's it. Any questions on any of this here? Hopefully increasing and decreasing is nicer than you thought it was going to be, for those that already looked at it. But that's it there.